Today we'll continue with the exercise 12.1 with the 23rd question. If you're looking for the previous questions, you'll find the link in the description below. Okay, so the question here is limit of fx when x tends to 0 and limit of fx when x tends to 1. As we see that the function is bifurcated at 0, the critical point is 0. This is where the function becomes different. In simple words, this is where the function becomes different. So let's put this on the number line for a better understanding. For all values smaller than 0, it is 2x plus 3. And for all values greater than 0, it is 3 into x plus 1. That means if you are going to find the limiting value of fx at 0, for less than 0, we'll have to take this function, and for greater than 0, we'll have to take 3 into x plus 1. So we'll have to go with left-hand limit, because for less than 0, it is a different function, and so it is limit, left-hand limit is limit of fx when x tends to 0 from the left side. And you can write this as limit h tends to 0 of f of 0 minus h. By 0 minus h, we mean that we are taking values smaller than 0. So 0 minus h is basically f of minus h. If f of x, this is the function f of x, for less than 0 is 2x plus 3, then what is f of minus h? Instead of x, put minus h. Okay. Now we can substitute the limit because the denominator is 1. Non-zero, so put h as 0 and you get the left-hand limit as 3. Now what is the right-hand limit? Right-hand limit in the same way is limit x tends to 0 plus of fx, wherein fx is, okay, because we are taking values greater than 0, let us take this h tends to 0, and because greater than 0, we'll take 0 plus h, means values bigger than 0, 0 plus something. And 0 plus h is f of h here. So the function bigger than 0 here is 3 into x plus 1. So we'll be taking this function. But now instead of x, we have h. So we'll write 3 into h plus 1. Now since once again the denominator is non-zero, put h as 0 here, the limiting value. And if the left-hand limit is equal to the right-hand limit, then we say that the limit of the function exists. And here the limit of the function is therefore 3. So we'll say therefore limit exists and limit of fx when x tends to 0 is 3. Now same way we have to find the limit at 1. To find the limit at 1, if you see, on the left hand side of 1 as well as on the right hand side of 1, the function is same. So you can directly find limit x tends to 1 of 3 into x plus 1, which is, because the denominator is non-zero, simply substitute the value x as 1 and you have 3 into 2, which is 6. So the limiting value for the function at 1 is 6. You can also do the same by taking LHL and RHL as we have done earlier. In that case, you would have to take x tends to 1 minus of fx. And now here, because it is 1 minus, we have to take value smaller than 1. So the function will be at 1 minus h for left-hand limit. So what is the function for 1 minus h? If it is f of x, this is the function. If it is f of 1 minus h, instead of x, we have to write 1 minus h. So this becomes 3 into 2 minus h, and substitute h as 0, you will get 6 as your left hand limit. And same way you can find the right hand limit by taking 1 plus h. Let us see, I'll put it this side. Right hand limit is x tends to 1 plus of fx, and here we are supposed to find for h tends to 0 if you take 1 plus h. And instead of x now we have to substitute 1 plus h. Simplify, you will again get it to be 6. The left hand limit is equal to right hand limit, so the limiting value is 6. This is the other method. This is also fine. You can do in this way also, because here the function is not defined in a different way. It is same for less than 1 and greater than 1 both. If it is different, we can follow the previous method. So now let's go to question number 24. Over here, the critical point is 1 and we have to find the limiting value at 1. So less than 1, the function is x square minus 1, and for greater than 1, it is minus x square minus 1. If this would be an MCQ question, we could simply substitute x as 1 to get the answer. Both the values are different. That means the limit of fx at x equal to 1 does not, x tends to 1 does not exist. However, if it is a subjective question, we will have to take limit, left hand limit. That means for smaller than 1, which we obviously write as x tends to 1 minus, we know that now. Now, if I write it in the form h tends to 0, we have to write x as 1 minus h, meaning we are taking values smaller than 1. So, wherever x in that function which is smaller than 1, let us write 1 minus h and simplify this. And then because the denominator is non-zero, substitute the limiting value which is 0. Okay? And same way for the right hand limit, which is for values bigger than 1. So over here we will have to take x as, yes, that is right, 1 plus h. Let's substitute 1 plus h wherever there is x for the function which is greater than 1. So it's going to be 1 plus h whole square minus 1. Simplify that and then put h as 0. Once again, the denominator being non-zero, we can directly substitute the limit. So if you put h as 0, you will get it as minus 2. Left hand limit is not equal to right hand limit. The limit of the function does not exist. Yeah, going to question number 25. As you can see, the function is modulus x upon x when x is not equal to 0. Let us first redefine this function. By redefining, we mean that we know that when is modulus x positive and negative. We know it is minus x for less than 0 and it is plus x for greater than 0. So we can change the way we are writing the function, and obviously x will get cancelled over here. So for less than 0 it is minus 1, for greater than 0 it is 1, and it is 0 for x equal to 0. So if we put this on number line, because 0 being the critical point, that is where the function is defined in a different way, we have for less than 0 minus 1 and for greater than 0 it is 1, and at 0 it is 0, but for limiting value we did not know what the function value is at the limiting value. So if I find the left hand limit, it is limit x tends to 0 minus of fx, and obviously we can convert this to h tends to 0. Because the limiting value is 0, it is 0 minus h. However, in this case, it doesn't make a difference because the function is constant value, which is minus 1. So when you find the limiting value for minus 1, it's going to be the same. And for right hand limit, x tends to 0 plus of fx, which is 0 plus h, values bigger than 0. 0 plus h means f of h, and because it's a constant function, it's going to be 1 only. The left hand limit is minus 1, the right hand limit is 1. So obviously the function is not having limit at 0. That means limit of fx is x tends to 0 does not exist. For question 26, again it is almost similar. Earlier one was modulus x upon x, now it is x upon modulus x. So whenever we write less than 0, modulus x will become minus x, and for greater than 0 it will become x. And so the function finally turns out to be the same. For less than 0 it is minus 1, for greater than 0 it is 1. And so once again you can find the limit in the same way. limit x tends to 0 from the left side, and again writing it as h tends to 0, f of 0 plus h, 0 minus h, because it is obviously value smaller than 0. And what is 0 minus h? Minus h. Wherever there is x, we are supposed to write minus h, but since it's a constant function, you have to just write down the function as it is. Minus 1 is the left hand limit. And the right hand limit, same way like the earlier question, x tends to 0 plus of fx, and converting it to h, because we have 0 plus, it will become 0 plus h. If you have 0 minus, it will become 0 minus. If it is 1 minus, it will become 1 minus. If it is 1 plus, it's going to become 1 plus. You just have to write h with it. Okay, so taking 0 plus h, the function bigger than 0 is 1. We are supposed to write h wherever there is x once again, but since it is constant, it's going to stay the same. And the limiting value will also be same. So left hand limit is minus 1, right hand limit is 1, and that's why the limit of this function also does not exist. Now we have to find the limiting value at 5, and here it is modulus x minus 5. It is not whole modulus x minus 5, it is modulus x minus 5. There is a difference. If it would be like this, the critical point would be 5, because this is when the modulus function would become 0, but over here the modulus function will be 0 when x is 0. So here the critical point is 0. Okay, so the critical point being 0, let us redefine this function for less than 0 and for greater than 0. For less than 0 it is minus x, and for greater than 0 it is x. So when I find the limiting value for less than 5 and for greater than 5, the function around 5, what is the function around 5? At 0 it is different. At 5, the left side of the function is also x minus 5, and the greater one is also x minus 5. So it is going to be the same. Whatever fx you write here, the same fx will come here. So this question can also be done like limit x tends to 5 of fx, because it is not different at 5. And simply putting the value, since the denominator is 1, which is non-zero, the limiting value turns out to be 0. However, if you do by this method, then as we discussed earlier, because it is 5 minus, we have to write 5 minus h. And what is the function for less than 5? It is x minus 5. Wherever x, write 5 minus h. 5 minus h minus 5. Okay. The function is this one. So in x I am writing 5 minus x. 5 minus h. Put the limiting value. So 5 minus 0 minus 5, or rather it is 0. Same way for this one. Since it is x tends to 5 plus, we need a value bigger than 5. So we will take 5 plus h. And wherever x, we have to write now 5 plus h. The function is the same. It will become 5 plus h minus 5. And substitute h as 0. 0 is the limiting value. Left hand limit is also 0. Right hand limit is also 0. And that is why the limit of the function is 0. Because both the values are same. This is one method. This is the other method. If you will see the textbook, you will find this one. And if you see some reference books like R.D. Sharma or so, you will get this method. So both of them are equally correct. Question number 28 reads as, suppose fx is equal to a plus bx when less than 1, and for greater than 1 it is b minus ax, and the limit of the function is equal to f of 1, limiting value at 1 obviously here. Okay, so we are supposed to find a and b. Now when do we say that the limit of the function exists? Limit of fx when x tends to 1 exists if the left hand limit at that point is equal to the right hand limit. So what is the left hand limit here? X tends to 1 minus of the function and x tends to 1 plus. And later on we can equate both of this to f of 1, or rather we'll write here only together. Okay. Now, if we put this on the number line, like we did in the earlier question, for less than 1 it is a plus bx, and for greater than 1 it is b minus ax. What is f of 1? 4. So we can write that here. So if it is limit x tends to 1 minus, we will write 1 minus h. Let's find this one first. Wherever x, write 1 minus h, a plus, or go to this one, it's the same, whichever is understandable, you do that. Now simplify and put h as 0, we will have the value as a plus b into 1 minus 0, which is a plus b. And finding the right hand limit, now because it is 1 plus, instead of x we will write 1 plus h. I have taken it as a whole equation. You can solve left hand limit separately, right hand limit separately, and equate it. Wherever x now, because we are looking for values bigger than 1, go to the function which is bigger than 1 and put x as 1 plus h. Put h tends to 0. That is wherever h put 0, you have b minus a. And this is equal to 4. That means both of these values. From this equation, actually we have 3 equations. A plus b is b minus a plus b is 4, and b minus a is 4. And you need only 2 unknowns. For finding 2 unknowns, 2 equations are enough. So we'll take a plus b is equal to 4 and b minus a is equal to 4 and find the value of a and b. So let's do that. A plus b is 4 and b minus a is 4. If we add both these equations, we have 2b is equal to 8. B being 4, a will be 0. Substitute obviously b in the one of these equations. So here are the values of a and b. In this question, these are constants, these are real numbers, and f of x is defined in so and so. This is a polynomial function with degree n. And we have to find 2 limits, when x tends to a1 and when x tends to a. So this question can be done like limit x tends to a1 of fx, and if you want to go with left hand limit, right hand limit, you can take a1 minus h wherever there is a1 and a1 plus h wherever there is a1. Or rather, I would substitute this a1 value wherever there is x. So a1 minus a1 will become 0, and 0 into any number is 0. So the limiting value of the first one, this one, is 0. Now let's find the limiting value for a. To find limiting value at a, wherever there is x, let's substitute a. And so the limit of this function at a is a minus a1, a minus a2 and a minus an, all values up till there. In this question, once again we have modulus x. So let's first redefine the function. The function will become, for less than 0 we know modulus x is negative, minus x. For greater than 0 it is going to be x. Now the question is, for what value of a the function, the limit of the function exists. So the critical point being 0, let us find it at 0. The rest all function part of the real number will not be a problem, because for greater than 0, if you take any number, the function is going to be x minus 1. It is going to have left hand limit and right hand limit same. So limit is going to exist. Over here also, for less than 0, if you take maybe minus 1, minus 0.5, minus 2, any real number smaller than 0 in the neighborhood, the function is the same. So the limit of this function will also exist at that point. only at 0. For less than 0 it is different, for greater than 0 it is different. So let's find for 0. So left hand limit is limit x tends to 0 minus of the function, and once again doing the h method. Wherever x, let us substitute minus h, minus of minus h plus 1. And substitute h as 0. This is h plus 1. Limiting value is 1. For right hand limit, you have to take x tends to 0 plus, because we are finding the limiting value at 0. Okay, let's take h tends to 0. F of 0 plus h, that means it is f of h wherever x, limit h tends to 0, wherever x, write h. Okay, so it is h minus 1. Substituting h as 0, it is minus 1. Left hand limit 1, right hand limit minus 1. The limit of this function does not exist at 1. It exists only at numbers other, the limit of the function does not exist at 0. It exists only at values other than 0. So, our answer will be for what values of a? It exists for all real numbers except 0. The limit of the function exists at all real numbers except 0. That should be our answer, because the left hand limit and right hand limit is not the same at 0. That means limit does not exist at 0. Okay, to the 31st question. If the function fx satisfies limit of fx minus 2 upon x square minus 1 when x tends to 1 is given as pi, we have to find the limiting value of fx at 1. Now, to find this, we first have to find fx. So, going to this part of the question where we are said that the limit exists, limit of this function exists. And if the limit exists, let's substitute 1 and see. When you substitute 1 in place of x, we find that the denominator is 0. If the denominator is 0 and the limit exists, that means the numerator should also be 0. If it is 0 by 0 form, only then the limit will exist, otherwise the denominator should be non-zero. Over here denominator is 0, so the numerator also should be 0. And that's why we have f of 1 minus 2 is 0, and so f of 1 is 2. See, why this is happening? It is not that we are substituting 1. We are taking values around 1 and the value is tending to 0. Okay, that is why the limit is existing. So, you shouldn't get confused with like, okay, 0 by 0 doesn't exist and how is that? Over here we are writing 0 upon 0. This is because when you are taking values near 1, you are getting values near 0. It's not actually 0, but it is tending to 0. So, if the denominator is tending to 0, the numerator also should tend to 0. That's what we mean. And that is why f of 1 should be 2. So, let us substitute this or find the limiting value for this one, which is wherever x, write 1. And so, what is f of 1? 2. So, limiting value of fx when x tends to 1 is 2. The critical points here are 0 and 1. The function smaller than 0 and the function greater than 0. 0 less than or equal to x. So, greater than 0. Function smaller than 1, yes, it is this, and greater than 1. So, when we are finding limiting value at 0, we have to take these two functions, less than and greater than, at 1, less than and greater than. It already says that if the limit exists, what is m and n? So, we have to take that if I take first at x equal to 0, left hand limit at 0 is equal to the right hand limit. This is what we should take, because it already given that the function limiting value is existing. Okay, so x tends to 0 minus of fx and x tends to 0 plus. We know if it is 0 minus, and if you are going to convert it to h, it is going to become 0 minus h, and if it is 0 plus and you are going to convert it to h, it is going to become 0 plus h. If not, you can simply write fx value and put x tends to 0. So, this is f of minus h. For less than 0, put minus h. M of minus h square plus n. Simplify and putting h as 0, we have it is n. Limiting value for the left hand limit is n. And for the right hand limit, wherever x, now we have to write 0 plus h meaning h, nh plus m, and again substitute h as 0. So this shows that when does this function have limit at 0? When n is equal to n. So this turns out to be when n is equal to m, then this limit exists. Same way we have to find for x tends to 1. Following the previous method, that is x tends to 1 minus and x tends to 1 plus for left hand limit and right hand limit. 1 minus means it is f of 1 minus h, and 1 plus means greater than 1, so it is 1 plus h. Wherever x, we'll write 1 minus h. Now we are talking about 1, so less than 1 and greater than 1. This is going to be the function less than 1. So in place of x, let us write 1 minus h, limit h tends to 0. Same way over here, but now because it is greater than 1 or the right hand limit, our function is going to be nx cube plus m. Wherever x, we have written 1 plus h. Now simplify and substitute h tends to 0. You will have, if you can take the whole cube or simply put h as 0. Here it is n into 1 cube, that is n plus m. N plus m is always equal to n plus m. That means this value, this function will have limit at 1 for all m and n, any real number for all m and belongs to R, you can say. Okay, whatever m and n, it is always going to exist because for every number n plus m is always going to be n plus m. This brings us to the end of the exercise, the limit concept. I hope you have understood the same. If there is any query, do write in the comment box. Do like the video, share it, and follow us on YouTube and Instagram. The links to the previous video are in the description below.